any other questions about this idea?
Sorry, right at that point where you've got the 0 there, where does the rectangle go for that?
Right here.
Okay.
It's a rectangle of height 0.
Yeah.
Yeah, that was that little red line there. Yeah. Because the right end point has height 0, so the rectangle ends up having height 0. But thank you for asking that, because again, I didn't explicitly explain what's going on there before. Yes?
Is there any usage of Riemann sum? Because when you need to calculate the area, you need to, because you know, area should not be negative.
Exactly. So usually when we apply Riemann sums, we'll have either one of two things going on. Either we have a situation where the graph just looks like that, right? In which case there is nothing happening below the x-axis. So usually if we're actually using the Riemann sum to calculate area, you won't have a graph that goes weirdly like that. It's the first thing to mention. The second thing is some applications of Riemann sums actually have a meaningful situation where something could be negative. I don't know if any of you have learned in physics that you can, if you have a graph of the velocity function, you can measure the displacement by taking the area under the velocity graph. I remember I learned that in high school physics. If you've learned that in physics, that thing is only true if you count areas below the x-axis as negative. Because if you go backwards for a certain period of time, if the velocity is negative for a certain period of time, that should end up being negative. That displacement should be in the negative direction. So there are certain applications, a lot of them being physics ones, where calculating negative areas is actually important. So yeah. And if negative areas aren't important, then you'll usually have a function that is only above, in which case it doesn't matter. Okay. Any other questions about this? These are important concepts, so I just want to make sure I got through them in enough detail. Okay. So the idea is, we introduced this symbol called a definite integral to represent what a Riemann sum is. Just sort of represent a Riemann sum. And you write the symbol like this, integral a b f of x dx. Now, the letter a represents where we're starting our integral. B represents where we're ending it. Right? So a always represents this point here, b always represents that point there. Right? Those are the x values where we start and end calculating the area. They tell you what interval we're dividing up into subintervals. Right? Here it was the integral from 0 to 3. The thing f of x in here is basically the same function f of x as this one. dx is sort of this abbreviation for delta x. dx represents what delta x becomes as the number of rectangles goes to infinity. So the idea is, of course, as you take more and more rectangles, this width of the rectangles is going to get smaller and smaller and smaller and smaller and smaller, and it's going to become what's called infinitesimal, infinitely small. And dx is an example of an infinitesimal. Again, understanding what an infinitely small object is sort of beyond this course a little bit. Like the metaphysics of infinitely small objects is definitely beyond the course. But the key thing you need to understand is that dx comes from the delta x. The dx is what comes from the delta x as n goes to infinity. Now, one thing to mention is there's this notion of what's called integrability, right? This is a limit. Limits sometimes exist and sometimes don't exist. If the limit exists, we say the function is integrable. We can integrate it. If the limit does not exist, we say it's not integrable. In this course, we're not going to have to worry about functions which are not integrable, but if anyone's going to go on to more math courses, you will see examples of functions which are not. Any questions about its definition of integral before I go on to using it? Okay. So, okay. So what I'm going to go into next is talking about how do we take a limit of a sum, how do we take an expression like this that we came up with, This is the sort of stuff that we came up with at the end of class, in section 5.1. How do we take something like this and turn it into an integral? How do we represent it as an integral? Well, what we do is we first figure out, what's the interval we're taking, right? And turn those numbers into the limits of integration. The bottom of the integral sign, the top of the integral sign. Then the lim and the sigma number we replace with the integral sign. The integral sign is abbreviation for a limit of a sum, for lim sigma. If you see an xi or an xi star, replace that with just an x. And if you see a delta x, replace it with dx. I realized example 2 here, there's something that was missing from the question, which is it doesn't say what the interval is. So in the textbook, if you actually open it to page 383, it says that the interval is from 18 pi to 2 pi. You'll see this thing written in the textbook. If I give you a question like this in the test, this will be there. It'll tell you what the interval is. Well, here's the interval of integration. That's the interval over which we're taking the area. And so those numbers are going to go on the top and bottom of the integral sign. This thing in front of here, we've replaced that thing with the integral sign. The next thing we're going to get is we're going to get cosine over something. And we're going to replace each of those xi's with just an x. And that delta x we will replace with a dx. So that's how we turn a complicated expression like this, involving a limit and a sum, into an expression just involving an integral symbol. This thing and this thing are two different ways of saying the same thing. This integral sign is just an abbreviation for saying that we calculate the area of each rectangle, we add them up, we take the limit. This abbreviation sign is an abbreviation for this. This cos x over x, that's a function whose graph we're using when we're calculating the area. Yes?
Is the interval pi?
Oh, whoa, thank you. I don't know why I wrote a 0 there. I was thinking pi, not writing it. We can also do things the other way around. We can take something that's written as an integral sign, written using integral notation, and try to turn it into something that's going to be written using a limit of a Riemann sum. We're reversing this process. And again, when we're reversing this process, we need to keep a couple things in mind. We need to keep in mind what's the formula for delta x. We need to keep in mind what's the formula for xi star, which I talked about at the end of last class. So, here we have the integral from 1 to 10, x minus 4 ln x dx. And we're going to try to express it as a limit of Riemann sums. Well, the first thing to mention is the integral sign becomes this thing, right? The limit as n goes to infinity of the sum I equals 1 to n. X will become xi star. And dx will become delta x. Right, so I'm basically reversing the process I did before. When I did it the other way around, in this example, the xi star became x, and the delta x became dx. Here, the x becomes xi star, dx becomes delta x. Then I need to figure out, okay, what is delta x? Delta x is b minus a over n, which is 10 minus 1 over n, which is 9 over n. What is xi star? Xi star is a plus I delta x, which is 1 plus I times 9 over n, which is 1 plus 9i over n. So I can write this as the limit as n goes to infinity, sum I equals 1 to n. Xi star is 1 plus 9i over n minus 4 ln 1 plus 9i over n times delta x, which is 9 over n. Sorry, I ran out of space on the board, which is why I wrote it down there. Oh, sorry, no, this bracket should be here, because the square brackets were these original round brackets. Right, but that's a way of taking an integral and turning it into a limit of a sum. So again, this notation is just an abbreviation for this notation. This one is the one we're going to be using throughout the rest of the course, and that's why I said working with this notation is not going to be particularly important. But what's going on now is I'm sort of talking about the fact that this is an abbreviation for this, right? So being able to sort of switch back and forth between one another is sort of an important part of section 5.2. Even though for the rest of the course, this is the one we're going to be working with. We're not going to be working with this one because this one's harder to understand. Okay. Any questions before we move on? Okay. So I'm going to abbreviate section 5.2 because we're definitely running low on time. I'm going to finish section 5.2 in Thursday's class. So this section here about evaluating Riemann sums, I'll get to that on Thursday's class. This is going to be sort of the hard way of doing things. And I'll talk about that a little bit more in Thursday's class. And again, this method is going to actually be the hardest way of doing things. It's called the method of exhaustion. I really like that name because it shows you how exhausting it is to do. It was called the method of exhaustion. It was the way that everyone calculated areas until the 16th century when calculus was invented. There is another easier way to calculate integrals, and that is if the integral is a nice shape like a triangle or a circle or a rectangle, we can actually calculate its integral fairly easily. Anyways, the thing I want to mention on this slide, and again, I'll go over this a little bit again because I'm sort of switching up the order. This slide makes not quite as much sense now as it will halfway through next class. Here, I'm talking about if I have the function y equals 2x minus 1, it looks like this, right? And this is y equals 2x minus 1. And I talk about this thing, the integral from, what does it actually say? Anyway, I think it was 0 to 3. Right, that says we're taking the area under 2x minus 1 from x equals 0 to x equals 3. Again, this is an abbreviation for a limit of a sum. And as I mentioned at the end of section 5.1, a limit of a sum gives you the area. As the number of rectangles goes to infinity, the approximation will become the actual area. Now, if I'm measuring this thing, or it couldn't have been 0. It could have, unless I... -2 to 2, there we go. I was like, that's not right. Anyways. So if we're talking about this integral from -2 to 2 of this graph, there's two different areas here. There's the red area, and there is, where am I marking? Oh, there. And there's the green area. We'll call the red area area 1 and the green area area 2. This integral is going to give you the area above minus the area below. Right? And again, this is the idea that I sort of talked about a little bit earlier when I was talking about how do you interpret a Riemann sum as an area. Well, the positive rectangles above the x-axis, will have positive heights. They'll have positive areas. Anything below the x-axis is a negative height, has a negative area. So when we're trying to interpret an integral, which an integral is just what happens to a Riemann sum when the number of rectangles become infinite, it's going to be the area above minus the area below. Any area above the x-axis counts positively. Any area below the x-axis counts negatively. So in general, if you want to evaluate an integral, what you've got to do is you've got to calculate the area above the x-axis and subtract the area below the x-axis. Now, of course, we can only do this if the shape is something nice like a triangle or a circle or a rectangle. If it's parabola, we're going to need some other method for evaluating the integrals. But if the shape is nice, we can evaluate it by just realizing that what it represents is the area above minus the area below. So this is the last thing I'm going to go over in today's class, is how do we evaluate integrals using area? Well, the idea is what we can do is figure out what the graph looks like. Graphing calculator is a great tool for doing this. So sketch the graph using a graphing calculator. Take the area between the graph and the x-axis and break it up into shapes that are either rectangles, triangles, or semicircles. Find the area of each shape and add the results up. So example 5 is from page 383 of the text. There is a picture, and we're using to calculate the area. And the picture looks like this. This is 6. So there's what the picture looks like. The idea is this is a function g of x, and we want to evaluate this thing. What's the integral from 0 to 7 of g of x dx? Well, the idea is when we're evaluating the integral, what we're doing is we're measuring the area above, and we're going from 0 to 7, and we're going to subtract the area below. So let's call this one A1, this one A2, and this one A3. The integral is going to be A1 plus A2 minus A3. We add the area above, subtract the area below. That should give you what the limit of these Riemann sums should get. That should give you what the integral is. So the integral is an abbreviation for that limit. That limit is the number of rectangles goes to infinity. That should be the same as the actual area. So area 1 is a triangle. The area of a triangle is half times the base times the height. Area 2 is also a triangle. Area 3 is a semicircle. The area of a semicircle is half the area of a circle. So it's going to be 1/2 pi r squared. Here, the base of this triangle is 2. The height is 4. Actually, I'm going to erase this and put it up in that corner. So here we have 1/2 times 2 times 4. This triangle, the base is 1, the height is 1. The radius of this circle is 2. So 2 times 4 is 8, half of 8 is 4.
Minus that.
Oh, thank you. So this is 4. Half times 1 times 1 is a half. 4 plus a half is 4.5. 2 squared is 4. Half of 2 is 2. So it's minus 2 pi. So that's what the integral is going to give you. 4.5 minus 2 pi. And that's because the integral always gives you the area above minus the area below. We can do the same thing with example 6 here. Right? It asks you to evaluate an integral. The only difference is they haven't given you a graph, which means you're going to need a graphing calculator or some other graphing electronic computer stuff to come up with a graph for this thing. Absolute value x minus 5. So the first thing to do is to sketch the graph of absolute value x minus 5. It's going to look like this. And if we want to measure this integral, what we're doing is we're measuring this red area. Let's call this area area 1, this one area 2. Oh, sorry. The height of these two triangles is both 5. And again, you can get all that information really easily with your graphing calculator. So this integral is going to be the first area plus the second area. The first area is going to be a half times the base times the height, so a half times 5 times 5. The second one is also 1 half times 5 times 5. 5 times 5 is 25, half of 25 is 12.5. This is also 12.5. When we add them up, we get 25. So this integral gives you 25. Okay. Okay, so that's it for the new material for today. Again, I sort of went over this stuff a little bit quickly. I will be able to do some more review of it next class. Again, what we've got for the last 15 minutes of class are a few group problems. Again, usually I will try to give more time for the group problems. Say the two group problems are there. There's just 2 of them. So take, 10 minutes-ish to work on these problems. And at the end of 10 minutes, I will go over the solutions to these 2. So here we want to find the Riemann sum for f of x equals sine x over this interval from 0 to 3 pi over 2 with 6 terms and right endpoints. What does it represent? And the next one is evaluating an integral. How do we evaluate that integral? And yeah, take 10 minutes to work on those. If you have solutions, want to show them to me, I can take a look. If they're correct, you can go home early. If not, I'll go over those in the last 5 minutes.